Okay, so catalysts are basically substances that they're not going to be consumed by the reaction. So basically, they're going to start off with what you end up with, right? They just kind of help speed up the reactions. So catalysts, they can be inorganic, so they could be like metals. They can be organic, or they could be biological, like enzymes. And all you're doing is you're speeding up the rate of the reaction, right? And often it's a result of optimizing the orientation. Okay. And so by optimizing that orientation, it lowers the activation energy. So you guys remember that the EA, right? So here you're just basically cutting that activation energy like in half or to some extent. Catalysts can be classified as homogeneous or heterogeneous. Homogeneous basically means like an example would be like enzymes in solution, right? So it's all uniform and everything like that. Heterogeneous basically means like you have a metal phase and you have a solution phase. So it's not the same type of thing, right? So you basically have a metal in solution, two different phases. Okay, so this is an example. If we take a look, so normally this would be the activation energy, the energy that we have to accomplish without a catalyst. And then a catalyst basically cuts it in half. The way I kind of like thinking of it is, okay, so you have this big ass hill, right? So you're pushing this car, you have to pick it up, push it over this big ass hill, right? But if there's a tunnel in the middle of the hill, doesn't it take a lot less energy to sit there and push the car through that tunnel rather than going up to the very top of the hill and trying to go down in that way, right? So it's less energy, right? And so that's basically what a catalyst does. It kind of cuts that in half. Okay. And then often, you guys pay attention up here, this is called the transition state, right? So often you will have a transition state to get to first before you can go down towards the reaction. And so sometimes the catalyst will affect that transition state. So it sets up that orientation, so it makes it easier for you can get to that transition state without having to work as hard. Okay, and so this is just an example of that here. So here, when you have a chemical reaction, this here serves as that transition state. So a lot of times what you'll do, you'll have a catalyst that helps orient it so you get to that transition state faster. Okay. So, for instance, you have O's, your O, N here. So it'll orient so that the C will attach to the O rather than the C trying to attach to the N or the C attached to both of the O's. So it sets up that orientation to make it a little bit easier. Okay, so this is just basically repeating exactly what I just said in different terms. So the catalyst is going to be regenerated, right? Meaning that what you're going to get at the beginning, you're going to end up with at the end. It's never going to be consumed. So, and it basically just alters the path of the reaction, making it lower in energy. And sometimes the catalyst can end up resulting in multiple steps, right? So you may end up having another intermediate that's quicker to get to than the one that you want, than the normal route. So this is just, again, showing you that the effects of a catalyst. So the red represents the activation energy normally, and then the blue represents, I forget. This here is the activation normally, and this here is the activation when there's a catalyst present. Okay. Again, we've talked about heterogeneous catalysts. And then these are just some examples. So here, the chlorine radical is going to be used as a catalyst. And it's the chlorine radical because it's just chlorine by itself, because we know that normally chlorine has to be diatomic, right? So here, this serves as an intermediate. So it actually will interact with the ozone, producing ClO and then oxygen. But then that ClO is then going to react with the oxygen. So you're going to recover just that Cl. Okay. So then that's an example of how catalysts can be utilized. So in 1995, Mario Manlini basically won the Nobel Prize because he actually was studying the ozone, and he actually realized that case of the chlorine radical is causing that. So a lot of our byproducts end up resulting in radical formation, and then so he modeled the depletion of the ozone in the Arctic area based upon the formation of that chlorine ion. Come here. So this is actually an enzyme, so a biological reagent. So this is a protein that it does a job. And so basically it speeds up the reaction of NADPH formation. And so one of the rate limiting steps is the formation of NADPH for the production of energy. And so this enzyme is responsible for just that speeding up of NADPH so that you can get ATP formation. And so this is just basically showing that process. And so this is the enzyme that does it. So it basically takes glucose 6-phosphate and then changes its form. And so it utilizes that NADPH, but by its utilization of that NADPH, you're going to end up getting the formation of this byproduct as well as your NADPH form, which ends up with ATP. Okay. We've talked about heterogeneous catalysts, basically 2 different phases. So that's like having a metal in gas or a metal in solution. So this is an example of, so this is the nickel surface. This is oxygen that's reacting on it. So it allows the oxygen to kind of bind in the right orientation for the ethylene to come in and attach to the oxygen. So it makes it a lot more efficient than having the 2 gases trying to find each other. Okay, and we kind of use this process in terms of the catalytic converter. So you guys use in terms of cars and stuff like that. So that's basically using catalytic converter. It's using a catalyst to sit there and allow for the combustion and then the production of clean emissions. Okay, so the other possibility is being an enzyme, biocatalyst. So proteins, like I just showed you earlier. And so how proteins basically will work is that they will have what they call is an active site. So then you have your substrates that are able to bind into your active site of the enzymes. So it allows it to be in the correct orientation for the 2 substrates to come together, and so that they can be active. And then, so then they come together, they activate, and then, so then you'll get whatever happens with those substrates. Okay. Questions? Concerns? Okay, so now we're on chapter 13. Okay, so we're talking about chemical equilibrium. So chemical equilibrium is used in tons and tons of processes, especially the body itself. So here's an example of the transport of carbon dioxide in the body, and it basically involves a chemical reaction. So we have CO2 plus water is going to yield carbonic acid, which ends up being broken down into its ionic component. So you get bicarbonate and the hydrogen ion. Okay. Now, this is an essential part of how we manage our body, keeps our pH the right pH is based upon this process. And if you guys take physiology, we talked about this product, the product of bicarbonate quite a bit, the production of bicarbonate in terms of balancing that nature, chemical reactions. So now these arrows here, see, you guys can't see what I'm pointing to, can you? These arrows here. So if you notice, the arrow is going in both directions. You have an arrow going one direction and an arrow going back in the other direction. So this represents equilibrium. That basically means that you have a reaction that's going in the forward and the reverse, okay? So when we talk about chemical equilibrium, it's basically a reversible reaction. Now, this reversible reaction is going to be happening consistently, right? And so here's an example where we have dinitrogen tetraoxide, and we're going to be making nitrogen dioxide, okay? Now, nitrogen tetraoxide is colorless. Nitrogen dioxide has a brown color. Now, what happens is that if you put this in a container, it's going to form what we call equilibrium. So you're going to get a brownish red color. It's going to result from it because you have that colorless component and you also have that brown component. And both moieties are going to exist, right? Because it's going to be constantly going from one to the other, right? So you're going to have the forward reaction occurring, and then you're going to have the backwards reaction occurring. Okay. So again, the double arrow represents equilibrium. It means that both you have a forward reaction and a backwards reaction. So a lot of reactions that happen aren't complete reactions, meaning that they're reversible. They're able to go both directions. So at equilibrium, the amount of the reactants and the products stop changing. It doesn't mean that they're the same, they're not equal to each other, but it means that the amount of them will stop changing. So there is one side could be favored more than the other in terms of equilibrium, and we'll talk about that here in a second. But it just basically means that you're not going to get a net change associated with it going back and forth. They're going to be stabilized. And so it's basically like a competition, right? So the forward is going to be competing with the reverse, and then you're going to get a point where you're getting a total net change. Now, but it's important to remember that it's a very dynamic process. So let's say, for instance, if we decide to take out the nitrogen dioxide, right? And so let's say we just siphon out a little bit of that nitrogen dioxide, and only that, because one is heavier than the other, right? So then what'll happen is that to get back into equilibrium so that there's no net change, right? It's going to push and make more nitrogen dioxide to compensate. Does that make sense? It's going to shift. So it's going to shift in this direction because you've removed some of that. Okay. That's right. If we remove, let's say we removed a little bit from the bottom, and that's the dinitrogen tetraoxide, right? Then in the case, it would shift to make more of that to compensate. And so then, so that there won't be a net change associated. Okay. Okay, so this is just basically showing us that, right? So at the starting point, we have the nitrogen tetraoxide. Before equilibrium, we're going to have more of the nitrogen tetroxide, and then we only have like very, very little of the nitrogen dioxide. As time goes on, we're going to change, right? And then until we reach that state of equilibrium where you get a total net change. And that's what this is showing you here. So at time zero, let's say time zero, we had no, at time zero, we had no nitrogen dioxide, but over time, as time increases, then we start producing more of that. At time 0, we have only nitrogen, dinitrogen tetroxide, and then it decreases until we reach that state of equilibrium. And this here represents that state of equilibrium where you don't get a net change of either of those two, okay? Now, you notice that they don't equal the same concentration, right? And that's very important to understand, okay? So this here represents the rate, this represents the time. So the rates of these will be equal at equilibrium. Not the concentration, but the rates will be, okay? Okay, so important things to remember. It's that competition that's happening between the forward and the reverse reaction. It's a dynamic process. You're getting a no net change, right? And the rates are going to be equal, right? So at that point, the rates are going to be equal to each other. Okay. And this is just basically saying what I just said. Now, some of the major misconceptions are the amounts of the reactants and products aren't normally going to be equal to each other. A lot of people think since they're in equilibrium, your product and your reactants are going to be equal to each other. No, it's not that. It's the rate, right? That's going to be equal to each other. Okay. The system, although it is at equilibrium, right? So that means it's going to be constantly moving. A lot of people assume that equilibrium is a static process. No, you're constantly moving. And that's kind of shown by us by removing it, right? So if we alter it, that means that it does that quick change. That means that you're constantly having things going back and forth. So have you guys ever been by the lake and like camped out by a lake or anything like that? Nobody's ever done that? Okay, so what we'll have to do is maybe we'll plan a trip that you guys get to camp out by a lake where it's really, really hot. So then you guys can feel the difference. So what happens is that the water and the water vapor, right, above the water are in constant equilibrium. So the closer you are to the water, the more moisture you feel because it's constantly, balancing each other out. It reaches that equilibrium point. Some is coming up, some is going back in. And you can kind of feel it when you're around the lake. Right? You can feel that equilibrium existing. Right? Often it's called lake effect, right? In Cleveland, so. Okay. So chemical equilibrium is a dynamic process. It's constantly happening. Okay, so we're going to talk about the equilibrium constant. So here's an example of bromium gas and bromium liquid. And so going from the gas state to the liquid state, that's a form of equilibrium, right? And so if it's captive, it's a closed sealed tube, you actually have a little bit of bromine gas and bromine liquid existing at the same time. And the rate of the liquid going to gas is going to be the same as the rate from gas going to liquid. Now, they're not going to be the same quantity, but the rate's going to be the same. Okay. So how do we do this calculations? So this is called the quotient. QC represents quotient for concentration. Now, the way that the quotient is defined is based upon a chemical equation, right? So we have our coefficients. So this is the coefficient for A, M represents the coefficient for A, N represents the coefficient for B, X represents the coefficient for C, and Y represents the coefficient for D. So the quotient is going to be equal to the products over the reactants. Okay, so it's the concentration of C raised to the X power and times the concentration of D raised to the Y power divided by the concentration of concentration of A raised to the M power and the concentration of B raised to the n power. M and V, no, they represent the coefficients for, yeah, okay? So they're gonna represent the coefficients that are in front of those chemicals, right? So if we have chemical A, M is how many that we have for a balanced chemical equation, okay? Yeah. Yeah. Well, we're using both X and Y in this case, yeah. So, but that was just to make it easier for that. Okay, so when we're talking about QC, we're talking about concentrations. So those concentrations have to be in molarity, okay? So it's going to be based upon molarity, okay? So again, the products are going to be in the numerator up top. The reactants are going to be in the denominator. Okay. So in this case of this hypothetical equation, we're going to use these we're going to get numerical values for our QC. Now, the QC is it's not the equilibrium, but it is a time point. It's like a look at a specific time point. So if we look at the QC at starting, we have no products, right? At the very beginning. Let's say we assume that we only started off with our reactants. So we look at time 0, then our QC is going to be 0, right? And then because we have no products formed at that point. Soon as we start getting products formed, right, that's going to be another time point. We could get another time point that's associated with that. And so we can look at it at various time points. And by looking at it at various time points, it can kind of help us find the position relative to equilibrium. Okay. So if Q is equal to K, K being the equilibrium, then we're at equilibrium. Q is going to equal the equilibrium constant, or K, at equilibrium. Okay. If Q is less than K, then you're favoring, right? You're favoring your reactants. Okay. So if Q is less than K, make sure I'm telling you, Q is less than K, you're favoring your reactants. That basically means that you have to produce more product. More product has to be formed for you to reach your equilibrium. Okay. If K represents the equilibrium constant. Okay. KC, yeah. Sometimes we have to calculate. Sometimes it's given. Yeah. Good question. Sorry, I got ahead of myself. It's a set value, right? Equilibrium is always going to be the same at a given temperature. So when Q is less than K, right, that means it's favoring the reactants. That means that you have more reactants than you have of your products. And so you're going to be pushing the reaction towards the products to reach equilibrium. QC is not equilibrium. QC represents, we're looking at the value at a specific time. Yes, it's like a timestamp. Exactly. Yes. Yes. And so KC, so at equilibrium, then this value is going to equal KC, right? Okay. So when K is greater than K, when Q is greater than K, then you're favoring the reactants. I mean the products. So you have more product than you have basically of your reactants. And so then it's going to be, the reaction is going to be pushing towards the react. Yeah, exactly. So you're going to be forming more reactants. That's right. Yeah. And so that means that in that case, the reaction is going to be going in this direction. That's right. So it's going to be going in that direction because we don't have as much reactants. Okay. So until it reaches equilibrium. Okay. So because at equilibrium, the arrows are exactly the same. They're balanced. Otherwise, you have one being pushed more than the other. Okay. Are you with me? Yeah. So this is just basically showing us that, right? So if we have a mixture where we have only the reactant, so here's our chemical equation, right? So we have a mixture where we have only the reaction at the starting point, right? So over time, until we reach equilibrium, then we're going to have an increase, but we're going to have a decrease. Okay, now here's our Q value. This is our reaction quotient, right? So our values is going to be less than the equilibrium constant until it reaches equilibrium. Okay. So then in the case where we have only our products, then our Q is going to be greater than the equilibrium constant until we reach equilibrium. Julie, you have a question? Yeah. So in this second figure, we have only products. So we're starting with only our products. So we're starting off with this now. We only have that. Okay. So as we have only this, that's what this is showing us. At time zero, we have only, at time zero, we have only our products. That isn't working out right. That is actually kind of backwards. But we're not producing, we don't have any, let's see, did I say this wrong? I think I wrote the equation wrong. It's actually flipped. Yeah. So my equation is written wrong. So this is our product, this is our reactant. So it actually should be flipped. So as we have only our product, then we have our Q is going to be greater than the value of this. So let me fix the equation real quick so that and then you guys need to fix it on your screen too. So you write it up the correct way. I need to fix it in my notes. Come on. Okay, is that better? Yeah. Okay, so here we have only the reactants, right? And then as the reaction happens, we're going to be making more product, right? So then our product is going to be increasing, okay? And then here we have only the product. We have no reactants, okay? And then as the reaction goes on, then we're going to be making more of our reactants. So in one case, this first case, the reaction is being driven in this direction, in the red direction, right? So that will be A, this part here. Okay. And the other case, the reaction is being driven in the brown direction, and that's going to be B. That's this over here. Okay. So this is B. This is A. What was that? Yes, it goes towards what it needs to make. And so you're driving the reaction towards what it needs to make. Okay. So, but the thing is that both of these are happening at the same time, right? So in theory, they're both happening at the same time. But if you have one starting from one side, it's going to be pushing the other one, although you're going to have a little bit going back to the formation of that. Okay, but the drive this way is going to be greater than this way until it reaches equilibrium. At equilibrium, they're going to be balanced. Okay. Yes, so the rate is going to be the same, right? It's always going to be the same at equilibrium. So at this point here, that's where equilibrium is reached. Then the rate is exactly the same. Okay. That's right. Equilibrium is matching rates, not concentration. Does that make sense? Okay. Okay. So if we look at our Q value, so if we write Q for this, QC for this reaction, then it's going to be what? We just want to write the equation. That's all. Just think about the equation. What is the equation? And then we'll talk about it for A and B. Concentration of what's going to be on top? The products. So it's going to be okay, and it's squared because of the coefficient. Okay, and then on the bottom, it's going to be the reactant. So it's going to be that's O2. They're worrying me over there. Okay. And so that's how we would use to calculate the quotient. So depending on the concentration that we are at that particular point, that will let us know. And then we'll compare that to our equilibrium constant. Okay. And if the equilibrium constant and the quotient are the same, then we're at equilibrium, right? If the Q is less than the equilibrium constant, then we have more, or not more products. We're favoring our, if Q is less than, yeah, we're favoring our less than equilibrium, then we're favoring, okay, that's right, we're favoring our reactants. So that means we have more of a reactants, and so it's going to be pushing the other way to counter-compensate, right, towards the products. Okay. Okay, so now important things to remember. Q at equilibrium is going to equal Kc, and that's just going to be that same equation that we have there, right? So the equilibrium constant is capital K. We do not want to mistake that for the rate constant, which is lowercase k. Okay. Although At equilibrium, the rate going in the forward direction is going to be equal to the rate going in the backwards direction. Okay, so but don't get them mistaken. The rate going in the forward direction is going to be equal to the rate going in the opposite direction, in the reverse direction at equilibrium. Okay, things that we want to keep in mind. For K, the concentrations must be those at equilibrium. So it's only at equilibrium when we're at equilibrium, right? And that kind of makes sense, right? Just by that name, right? Okay, otherwise it's called Q, right? And Q is when we're not at equilibrium. Okay, but Q can equal equilibrium. Okay. Okay, so the equilibrium constant is independent of the starting amounts of reactants and products. So it's not dependent on the starting amount. Okay. The equilibrium constant is dependent on temperature. Okay. So you're getting this trend. Temperature plays a huge part in all of this crap, right? The value, and that kind of makes sense. If you guys are like, again, if we're by a lake, if it's really cool by the lake, right? The rates going forward and backwards is going to be slower than in the case of when it's really, really hot, right? Doesn't that make sense? Yes, okay. Okay, the magnitude of equilibrium constant indicates the extent of the reaction. In other words, it just says which side is more favored by the side. So if the value is really, really big for the equilibrium constant, that means the overall reaction has a favorite towards the products. That's right. If the value is really, really small, then we know that it's favoring the reactants. Okay. And the units are going to be unitless for K. So K and Q are going to be unitless. Okay, so we're not going to have any units associated with it. Okay, so if K is very small, the mixture contains mostly reactants at equilibrium. If K is very large, the mixture contains mostly products at equilibrium. Okay, the value of K is given. I'm sorry, the value of K gives no indication whether the reactance is fast or slow. Okay, so it has nothing to do with that concept of speed because it's not going to tell us that. Okay, I need to fix that. Okay, so at a constant temperature, the following equation has a Kc of 4.18 times 10 to the minus 9. Calculate Q and identify the direction the reaction will be proceeding for a mixture of 0.200 molar of HBr, 0.0100 molar of H2, and 0.0100 molar of Br2. I'll let you guys work that out. Okay, so our Q is going to equal. So it's what over what again? Products over reactants. Okay, so our products, the concentration of our products is, so we have 0.0100 times 0.0100 divided by 200 squared So then that's going to equal 0.025. I have 1 0 off. Okay, it's not behaving. Erase. There we go. Okay, so is our Q greater than our equilibrium constant, or is it less than our equilibrium constant? It's greater, right? Because here's our equilibrium constant, right? So who are we favoring? Our reactants or our products? So we're favoring our products. So we're going to be pushing which way is the reaction going to be going then? Okay, so it's going to be going to the left, this direction, right? Okay. So I guess let me reframe how I said it, right? Because it says it's favoring the reactants. So in other words, it's going to be going towards the reactants, right? So we have more product than we have reactants. And so we're going to be going towards the left. Yes, because you're going to be pushing towards the reactants. So you're going to be moving towards it. So let me use that terminology correct. That's my bad. Yeah. So right now we have more product. And that's where when I say I have a bad habit, I look at it as there's more products. So right now we are favoring the products because that's what we have mostly of. But we're moving towards the reactants. We're going to be producing more reactants. Okay. That's right. Yeah. Okay. Does that make sense? So right now we're more abundant on the products. So we're going to be moving to the reactants. So you would make, in this case, the top arrow would be going, yes, be larger in that case, because it's pushing towards that. Yes. Right now, but that's only temporarily, right? Because yes, because you're saying, hey, we started out with more. So this rate is faster than this rate, right? You could use it just, I would just show the arrow going in one direction, kind of like I have it shown now, right? So then that lets me know that we're pushing towards it. Because overall, if you look at the reaction altogether, yeah, you have this little arrow, but you have an arrow that's going to be favoring the net reaction is going to be going towards the, does that make sense? Okay. So, but in theory, you have both ways going, right? You're going to have a small one going in one direction and a larger one in the other. Okay. Sorry, larger going this way and a smaller one that. Okay. Got carried away. And okay, so homogeneous equilibrium is when all the reactants and products are all the same phase. So then what is heterogeneous? When you have different phases. Okay. Most commonly, you're going to either have a liquid phase or a gas phase or a solution. Yeah, that's right. Well, that one had both liquid and gas, so that would be hetero, right? Okay. So the reactions, the reaction quotient can include either the concentration or it can include pressure. So if you're using pressure, you want to use pressure consistently. If you're using concentration, you want to use concentration consistently. Somebody come by. Okay. Okay. So for the gas phase, right, you're going to have the Kc. That's going to be your equilibrium concentration, your equilibrium constant for concentration. Kp is going to be for partial pressures. Okay, and their values are going to be different. Okay, and I'll show you that here in a few minutes. Holy shit, skip the whole slide. Okay, so this was adopted. Okay. So here's the example for the equilibrium constant for pressure, right? So it's going to be, again, calculated the exact same way. And so the equilibrium constant for pressure is going to be equal to Kc times RT delta N, where delta N is going to be your number of moles when you use PV equals nRT. So delta N is going to be the change in number of moles. Right? Okay, so it's going to be the sum of the coefficients of the gas products minus the coefficients of the gaseous reactants. R is going to be 0.08206, and temperature is going to have to be in Kelvin. Okay, so this will allow us to convert from pressure to concentration. K, pressure equilibrium constant at pressure to concentration. Okay, are you with me? Okay, and so now what I'd like you guys to do is write the equilibrium expression for all of these. So if it's in concentration, write the equilibrium expression for concentration. If it's in pressure, then write the equilibrium for pressure. Right. Okay, so you have answers? Yep, you're just writing the equation for equilibrium, right? So you're saying Kc is going to equal, in this case, you have to use pressures because they're gases, right? So Kc is going to equal P squared, and that's for NO2, divided by P, partial pressure of N2O4, RT at the bottom. Right? Okay, and then for 2, it's going to be this value, Kp. So you don't have to include that RT component. And then down here, we've basically flipped the equation. So then you're going to flip the reaction. Right? So then this guy's going to be Kc. It's going to equal thank you. PNO2 squared over PN2O4 . And you guys know that that's just defining what pressure it is. So RT. And then this guy is just going to be this guy flipped. So Kp is going to equal P in 2O4 divided by P NO2, and that's going to be squared. Okay. Okay. So let's stop here. But before we stop, you have the opportunity of getting extra credit. Actually, you have two opportunities of getting extra credit. One for tomorrow, there's the Black History event at noon, and it's up on your Canvas shell. So you guys just hit the link for that. And then the second one, there is a presentation that I'm giving on Saturday. And so you'll have another chance of getting 5 extra credit points on Saturday. Dealing with careers. I'm pulling it together out of my butt tonight. So I don't know when I'm going to have time to do everything, but we'll get it all done. Yeah, I'll be putting it on the Canvas shell tonight. So once I remember to do that. So extra credit, 2 opportunities of extra credit. Saturday, I'll be giving a careers on health careers, talk on health careers. And then tomorrow, there's the Black History event at noon. And the link is already up on Canvas for that one. Okay. Questions, concerns, cash? I don't know. Okay. Did you guys hear that, Abel and Marisol?
I got it.
Okay. Yes.
Okay. So I will see you guys, Abel and Marisol, on Tuesday for the lab, since I screwed up. And let's make it at 11 because they don't get out until a little bit late. And so we'll just put you guys in the back to get the labs done.
All
Okay,
right.
that sounds good.
Okay. Okay, you guys have a good night.
All right. You too. Bye-bye.
Bye-bye.